Hi everyone, and welcome back to the channel. Today, we're taking a deep dive into one of the most fascinating and powerful places on Earth, Yellowstone. You probably know it for its incredible geysers like Old Faithful and its amazing wildlife. But beneath all that beauty lies a massive supervolcano, one that has shaped the continent. And the big question scientists are always asking is, when will it erupt again? To answer that, they have to look back in time, like geological detectives, piecing together the story of Yellowstone's explosive past. So, how exactly do they do that? How can they know what happened millions of years ago? Well, that's what we're going to uncover today. It's a story of rocks, ash, and some seriously clever science. First, let's get a sense of scale. Yellowstone isn't just one volcano, it's a massive volcanic system. We're talking about a caldera, which is a huge cauldron-like crater that's about 45 miles long and 30 miles wide. That's bigger than most cities. This caldera was formed by unimaginably huge eruptions in the past. The most recent major one, about 631,000 years ago, was 1,000 times bigger than the 1980 eruption of Mount St. Helens. It blasted so much ash and rock into the atmosphere that it covered a huge portion of North America. Imagine an ash cloud that could block out the sun for weeks, maybe even months. That's the kind of power we're dealing with. And this wasn't a one-time thing. There was another massive eruption about 1.3 million years ago, and an even bigger one, the Huckleberry Ridge Tuff eruption, about 2.1 million years ago. That one was over 2,500 times larger than Mount St. Helens. So, we have these three gigantic events. The first clue for scientists is the caldera itself. Its sheer size tells them something enormous happened here. But how do they find the evidence of these eruptions, especially the ones that happened so long ago? The primary evidence is right under our feet. It's all in the rock layers. Think of the ground as a giant history book, with each layer of rock representing a different page or chapter. When Yellowstone erupted, it didn't just spew lava. It threw massive amounts of volcanic ash, tiny particles of rock and glass high into the atmosphere. This ash then settled back to Earth, blanketing the landscape. Over thousands of years, more layers of sediment, like soil and sand, cover that ash layer, preserving it. So, geologists can go out, sometimes hundreds or even thousands of miles away from Yellowstone, and dig down. They look for these distinct layers of ash. It's like finding a geological fingerprint. When they find a layer of ash, they have to confirm it came from Yellowstone. How? Volcanic ash has a unique chemical signature, like a DNA profile for a volcano. The specific combination of minerals and elements in the ash from a Yellowstone eruption is different from the ash from, say, a volcano in Oregon or California. Scientists collect samples of this ash and take them back to the lab. They use sophisticated equipment like mass spectrometers to analyze its chemical makeup. By comparing the chemical signature of the ash they find in places like Nebraska or even the Gulf of Mexico to the rocks inside the Yellowstone caldera, they can say with certainty, yep, this came from Yellowstone. It's incredible detective work. Once they've identified the ash layer, the next big question is, how old is it? This is where radiometric dating comes in. You might have heard of carbon dating, which is used for organic things that were once alive. For volcanic rock, scientists use a similar method, but with different elements. A common one is potassium-argon dating. Volcanic rock contains the element potassium. A tiny fraction of that potassium is a radioactive isotope called potassium-40. Over a very long and predictable time, potassium-40 slowly decays and turns into argon gas. It's like a super slow, super reliable clock. The tick-tock of this clock is its half-life, which is about 1.25 billion years. That means it takes 1.25 billion years for half of the potassium-40 in a sample to decay into argon. So, when a volcano erupts, the molten rock is so hot that any argon gas that was already there escapes. The clock is essentially reset to zero. Once the rock cools and solidifies, the new argon gas produced by the decaying potassium-40 gets trapped inside the rock's crystals. Scientists can take a rock sample, carefully measure the ratio of potassium-40 to argon gas, and use the known decay rate to calculate how long it's been since that rock cooled down. In other words, they can tell you when the eruption happened. This is how they pinpointed the dates of Yellowstone's major eruptions: 2.1 million, 1.3 million, and 631,000 years ago. It's mind-blowing that we can look at a tiny crystal in a rock and figure out its age with such precision. But dating the ash is just one part of the puzzle. Scientists also want to know how big the eruption was. To do this, they have to figure out the volume of material that was blasted out. This means more field work. They map out how far the ash layer spreads and how thick it is in different locations. It's like creating a 3D map of the ancient ashfall. For example, they might find a layer that's a few feet thick near Yellowstone, but only a few inches thick hundreds of miles away. By collecting all this data and feeding it into computer models, they can calculate the total volume of ash that erupted. This is how they determine that the Huckleberry Ridge eruption ejected over 2,450 cubic kilometers of material. To put that in perspective, that's enough stuff to bury the entire state of Texas 5 feet deep. That's the definition of a super-eruption. Another amazing set of clues comes from right inside Yellowstone National Park itself. The park is filled with what geologists call tuff. Tuff is a type of rock formed from consolidated volcanic ash. The lava flows and ash deposits from past eruptions have created massive cliffs and canyons made of tuff. The Lava Creek Tuff, for example, is from the last big eruption 631,000 years ago. By studying the thickness and composition of these tuff formations, geologists can get a direct look at the eruption's products. They can see different layers within the tuff that might represent different pulses or phases of the eruption. It's like reading the eruption's autobiography written in stone. They can see how the magma's chemistry changed during the eruption, giving them insights into what was happening deep inside the magma chamber. Scientists also use more modern techniques to look beneath the surface. They use seismometers, the same instruments used to detect earthquakes, to create a picture of what's happening underground. Yellowstone is one of the most seismically active areas in the country, experiencing thousands of small earthquakes every year. These quakes are caused by the movement of magma, hot water, and gases deep within the Earth's crust. By tracking these tiny tremors, scientists can map the location and size of the magma chamber. It's like giving the Earth an ultrasound. They can see where the molten rock is, how it's moving, and whether it's rising towards the surface. They also use GPS to track ground deformation. If the magma chamber starts to fill and swell, it will actually push the ground up. These GPS stations are so sensitive they can detect changes in elevation of just a few millimeters. So, they have a real-time monitoring system for the volcano's breathing. By combining all these methods analyzing ancient ash layers, radiometric dating, mapping the volume of eruptions, studying the tuff inside the park, and using modern seismic and GPS monitoring, scientists build a comprehensive picture of Yellowstone's past. The data from past eruptions helps them understand this cycle. They've learned that the time between the three major eruptions was about 800,000 and 669,000 years. Since the last one was about 631,000 years ago, you might think we're due for another one. But volcanoes don't run on a strict schedule. These are just averages. Right now, all the monitoring data from the Yellowstone Volcano Observatory shows that the system is behaving normally. There's ground uplift and subsidence and constant earthquake swarms, but that's all part of the normal activity for a living, breathing volcanic system like this. There are no signs of an imminent eruption. So, the next time you see a picture of Old Faithful or the Grand Prismatic Spring, remember the incredible story that lies beneath. The story of a geological giant pieced together by dedicated scientists using clues hidden in plain sight in the rocks, in the ash, and in the very ground they walk on. It's a powerful reminder of how dynamic our planet is, and how science can help us understand its most powerful forces. Thanks so much for watching! I hope you found this deep dive into Yellowstone's secrets as fascinating as I do. If you enjoyed this video and want to learn more about our amazing planet, please hit that like button and don't forget to subscribe and turn on notifications so you don't miss our next adventure. See you in the next one.